Welcome to MEI Modelling with Algorithms. We're on the topic of graphs and networks 2, minimum spanning trees and shortest paths, and we're on video 2.4, shortest paths. So let's describe the type of problem that we're going to be trying to tackle in this video. Imagine we've got a network like that and we're trying to get from A over here on the top left to F down here on the bottom right in a way that has the least total weight. Now, of course, these weightings could be times or costs or distances, whatever it is, but we're trying to minimize that total weight. So you might want to just pause the video for a moment now and see if you can kind of do this by sort of just looking at it, and then we'll have a look at a formal algorithm that can tackle this problem after that. So if you do think you know what the shortest route is, you might want to just make a note of it, and then we'll see if you're right later on. Let's just say a little bit more about the problem firstly. So we'll always have a network of locations, and we want to know what is either the shortest distance or shortest time or possibly lowest cost to go from one point on the network to another. It'll be the same algorithm every time. We'll talk about that later. We'll always really be referring to the weights as the thing that we're dealing with. So when we talk about the shortest path, it may be that we're dealing with distances, but we might be talking about times or costs or anything. So shortest is being used slightly loosely there. The algorithm that we're going to use is called Dijkstra's algorithm. It was developed in 1956, published 3 years later, and this is the algorithm that we're going to be using in this course in order to find the shortest distance between 2 points on a network. Now, this is the algorithm itself. It may look a little bit daunting. What I'll say is I will give you a moment to read through it, but I really wouldn't expect you just by reading that to fully understand it. But it's worth just having a few moments just to read through it to get some sense of what's going on. And then we'll do a worked example, a very carefully worked example, and then it should become clear what is actually happening. One thing you may wish to do here is take a screenshot of this page and have it there so you can refer to it. So when we're actually carrying the algorithm out, if you need to, you can look at these steps. Now, one thing that makes it much easier for us to carry this algorithm out is that we will always label each node with one of these special boxes that records particular pieces of information that are used as part of our working and also form actually part of the final result as well. So in this part of the box we'll write down the order in which the nodes are given their permanent labels. In this box we'll actually write these permanent labels. I'll explain more about what we mean by the permanent labels later. And this bigger box at the bottom is for our temporary labels. These are our sort of working out values that may become updated as we go on. So this is the same problem that we saw earlier, and the first thing we're going to do is actually put these boxes in. Down here on the bottom left there's just a little key just to remind ourselves of what the parts of that box do, and so we're ready now actually to carry out Dijkstra's algorithm on this network. So the first thing we need to do is deal with this start node A. This is obviously the first node to be labelled, so that gets an order of 1, and its permanent label, and the permanent label will always be the shortest distance from the start node to the current node. So obviously for the start node itself, its distance is 0, and it's never going to have any temporary labels. So the next step then is to look at anywhere we can now get to from the node that was just made permanent and update the temporary labels from there. Okay, so we know it's possible to get to A in a distance of 0, and because I can then get from A to B in a distance of 3, that means I can record a temporary label of 3 there. And likewise for node C, I can also get to that one from A. That is given a temporary label of 5. So now we've done all the updating of temporary labels, what we do is we look at all of the nodes which have got temporary labels but have not yet been made permanent, and whichever one has the smallest temporary label, we now know that that is actually the shortest distance from the start node to that particular node. And so that means that we can say that B now has a permanent label of 3, and it is the second one to be labelled, so we give it an order of 2. Okay, so then we're repeating the steps again. I've just made B permanent, so I need to look at everywhere I can get to from B that isn't yet permanent itself and update the temporary labels. So here we have a distance of 3 to get from B to D. Okay, so that means that if I add that 3 on to the distance that we know it is from the start to get to B, that means that I know I can get to D in at least, or at most, a distance of 6. Okay, so I take that permanent label and I add that weight on to get that temporary 6, and then here, if I was to go from B to C, if I take the 3 and add on 1, that gives me 4, and this is where I need to be careful. I need to compare that 4 with the 5. Because that 4 is less than 5, I'm going to update. If it wasn't less than 5, then I wouldn't. Because we're trying to find the minimum distance here, it's only worth updating these if I found something better than I had before. So now I know I can get to C in a distance of 4. Okay then, so that's all the updating done. I now have to look at these temporary nodes now and decide which one I can make permanent. So this one's got a temporary label of 6, this one has a temporary label of 4, and so this is the one which is now the one I can make permanent. So that gets a permanent distance of 4, and it was the third one to be given the permanent label. Right then, so where can I get to from C? Okay, well I can get to node D by taking this 4 and adding on this 1. I know I can now get to D in 5. That's smaller than 6, so I will update it. I can get from C to E in 3, so adding that onto the 4, that means I can get to E in a distance of 7. And that's all the updating done from there. Which nodes are now temporary? It's these two, so I need to look at that one and that one. Which one's got the smallest temporary label? It is node D, so that gets a permanent label now of 5, and it was the fourth one to be labelled. So now from D to F, I do 5, add another 5, which is 10, so I can get to F in 10. Or I can go from D to E in 5 plus 1, so that's 6. I will update that. And so which ones are temporary now? I've got E and I've got F. E is the one which is the least, so that is the next permanent node, and that gets an order of 5. Okay, so where can I get to from E? Well, the only temporary node left is F. If I do 6 plus 3, that gives me 9. And then I have a permanent label here of 9. And this was the 6th node to be given the permanent label. So that completes at least the first phase of Dijkstra's algorithm. Everything is now, all the boxes are now completed. Every node's been given a permanent label. As soon as the place I'm trying to get to has a permanent label, of course, I can stop. Usually that will be set up so that will actually be the last one that gets made permanent, but it's not necessarily always going to be the case. So what I know at this stage is it is possible to get from A to F in a distance of 9. And that is the best I could ever do. What I don't actually know, and what I can't see straight away at least from this, is how I actually get there. So the second stage of the algorithm now is to trace backwards from the final node back to the start and to actually find the shortest route that is actually going to be used. So let's start with f, and what we need to work out is, because we may not remember from what we were doing earlier, which of these two arcs was actually used to get there. And the way to do it is, if you think, well, it's got a label of 9. If it came from here, that would mean that if I add this number, add on 5, I should get 9. And of course I don't. If I do 5 plus 5, I actually get 10. So it can't be this. This can't be the arc that it was used, because it's inconsistent with these numbers. So let's check with this one. If I do 6 plus 3, yes, I do get 9. So this is the one that must have been used. So I can add this onto my path. I then just repeat that process. So I'm either coming from here, 5 plus 1 to make 6. Yes, that seems to work. Let's just check here. 4 plus 3 would be 7. That doesn't work. So this is clearly the way that I came to get from to E. I came from D. Okay, here I've either got 3 plus 3 to get 5. No. Or 4 plus 1 to get 5. Yes, that works. So I definitely came that way. How did I get here? Well, it's this one which is consistent, because 3 plus 1 gives me 4. And then clearly here 0 plus 3 is 3. And now I have the shortest path. And so to finish off, I write down what that path is, A, B, C, D, E, F, and I write down its weight, which is 9. So here's another one. It's probably worth, at this stage, if you try and do this one by yourself. Again, I'd recommend taking a screenshot of this if you can, and maybe printing it if that's available to you. Be very careful with the steps. Make sure you're looking at the steps. The one thing, and I'll mention this later, but the one thing I really must emphasize is that when you're choosing the next permanent node, you have to look at all the current temporary nodes. So all the nodes which have got temporary labels that haven't yet been made permanent. It may be that some of those have been sitting there for a while and not been updated. It's not just going to be ones that are connected to the most recent permanent node. So just be careful, because I think in the previous example that might have just been the case. It might just have happened to be the case that they were always ones that had just been dealt with. But do check for all of them. Okay, so have a go at that. Pause your video, see if you can do it by yourself, and then in a moment I will reveal the solution. And here it is. So one thing I should point out here, sometimes you see these labels being crossed out when they get updated. I would actually advise you not to do that, because actually often in exams they will tell you not to do it, and the reason is, of course, an examiner would want to be able to tell the difference between something which you've done in error and wanted to cross out because you didn't want it to be marked, or something like this where it is actually part of the working and part of your working was to cross it out. So I would actually advise not to do what's done on that screen by crossing it out. Just separate them with commas. The one which is furthest to the right would always be taken as the most recent one. Look carefully at that. If you didn't get exactly what's on there, so not just the same route, but also look at all the permanent labels, look at everything, all the temporary labels. If there's any difference in what you've got to what's on there, then go back and have a really close look at the algorithm again and make sure that you can get that to work. So you may have tried to think as we were doing this how this thing is working. We're going to discuss that a little bit now. Firstly, just a reminder of what these things represent. Alright, so they could be times, they could be costs, or what have you. But whatever it is, we're trying to find the least total of those things for the route that we take. So when we've got these labels, these temporary labels, and in particular these permanent labels, they are actually telling us something about a route from the start to the current node. And so even the temporary labels are telling us it's possible. There's something which is possible to do. The permanent one is when we are sure that that is the least possible one that we can choose. But we need these temporary labels along the way so that we can sort of compare when we get a new possible temporary label, compare it with what we've already got, and that way we can be sure that we've got the the actual shortest one in the end. Um, and so the key thing really is that the point at which we make the thing permanent, at that point we've basically checked all the possible routes that could ever be done, that could ever be um, shorter than what we've currently got. So at that point we become certain as to the shortest route for the across the whole network. And of course, having made one node permanent, that then allows us to think about temporary labels on the nodes which neighbour it. We talked a little bit earlier about why the first node gets a permanent label of 0. I think that should be fairly obvious. And then when we think about how we trace back, well, again, we were just looking for something that was consistent with the numbers that were there. All right. And so once we found a route that follows that and has that total distance, that must be the shortest route because we know that that's the shortest distance. And just a few more things to say about Dijkstra's algorithm. We mentioned that it may be the case that we sort of, in a sense, finish early, so we might not end up labeling every node. As soon as we've got to the one that is our final node, as soon as that's permanent, then we can stop. Occasionally, you'll see Dijkstra's applied to directed networks. That's fine as long as you respect the direction of the arcs. It works on direct networks as well. Now, in terms of efficiency, in a sense, you get a lot of information for free when you do Dijkstra's that maybe you don't need. If you think about this on a much larger scale, what's going to happen is you're going to end up doing an awful lot of unnecessary work, or probably unnecessary work at least. If you've ever used a sat nav system or seen a sat nav system working, it very quickly finds the shortest route between, say, two places in the country, and there must be all sorts of different routes. So it would just be impractical, really, to do this using the full Dijkstra's algorithm. So there are other algorithms out there which are possibly heuristic algorithms, and so they're not guaranteed to give you the shortest route, but they will actually complete in a reasonable amount of time. There is something called dynamic programming, which is something which may come later. Um, and one thing to watch out for, I mean, you shouldn't expect to be given a question like this really, but just to be aware of this, that there could be networks with negative lengths. For example, if they're representing cost and you actually profit from taking a particular route. The problem, of course, then is that you would then just decide to go back and forth, or according to the algorithm at least, you just go back and forth along a route. Now, in practice, there'd be some reason why you couldn't do that, I guess, but it basically, the algorithm is not going to work if you have negative values anywhere. Now, a few things that you really must pay attention to, so to avoid making these sort of mistakes yourself. Um, you must actually obviously remember all the steps, so make sure you add the new arcs onto the permanent label. Something we mentioned as we were doing it earlier, only replace the labels if they're smaller. Make sure you're just working from the last label that was made permanent, don't go any further than that. The thing which I think is actually the most important thing, and the thing which I see, the mistake I see people making more often than any others really, is this idea that when you're considering the non-permanent nodes in order to decide which one to make permanent, make sure you look at all of the ones which are currently temporary nodes, not just the ones that have been updated in the previous step. And I suppose this final one is just a case of saying, well, don't worry. Like so many times in decision maths, you might find that you've got two equally good choices. This can actually happen when you're carrying the algorithm out in the first place and choosing which one to make permanent, but also when you're working backwards. It doesn't matter. If you've got two equally good options, you'll be able to use either, and they'll both give you a valid solution. They won't necessarily give you the same one, but they'll both give you a valid one. So that concludes the topic of graphs and networks 2, minimum spanning trees and shortest paths.